Good.
Okay, we are now recording. So, Tom, do you want to say something?
No, I'm fine.
Okay. So, share screen. That one. Okay, you should be seeing it about now.
Got it.
Got it? Okay, I'm going to put this on this mode here. Okay, now it should be even bigger. So here is where we left off last Thursday. We were talking about optimization problems. We were talking about constrained versus unconstrained problems. And just to recap a little bit here, make this sound like it's more relevant than it might seem on the surface. We showed some structural optimization examples that had been solved, I think, in the 50s, using not using fancy computers, because they didn't have fancy computers back then, but they had some computers, but they were the size of a house. And we talked about the idea, and this is a really important concept I want everybody to remember, the idea of a design space, a multi-dimensional design space. In the case of these examples I showed you, these were simplified to two-dimensional design spaces, which is good for illustrating how the idea works. But you have an objective function, which you're either trying to maximize or minimum. In this case, because the objective function is weight, we're trying to minimize. You plot out the objective function as a function of your two design variables, in this case A1 and A2, and you can start thinking of this in terms of a mountain where low weight is at the bottom of the mountain, high weight is at the top of the mountain, so you're trying to get to the bottom of the mountain. And then you have these various constraints which relate the maximum stress that a structural member can handle. You put that on this graph, and all of a sudden it becomes very easy to start visualizing how you can cordon off certain areas where you can have design and certain areas where you can't have design. And then once you've defined that feasible region, it's very easy to find the bottom that's within the feasible region, and that gives you what the minimum weight possibility is. We liken this to climbing a mountain like Alpe d'Huez. We talked about the blindfolded skier trying to climb up a mountain, trying to find the top, or trying to find the bottom, going down a pit, and then we played a game. And the game was made a lot easier by Jaewon, thank you, because he was smart enough to figure out that just pick the biggest or the smallest x1 because the equation would be dominated by that fourth power. Regardless, the point of this exercise was just to show that what it's like to be blindfolded trying to find the maximum or minimum of a function, which is often the case when you're designing things in the real world. Then we got here. So constrained and unconstrained problem. So if you have some function x and it's a one-dimensional design space x, design vector x, and it's an unconstrained problem, then it's very straightforward to go ahead and take the first derivative of the curve at every point, set it equal to 0, and then you would find the points where the slope of that curve was 0. And then by taking the second derivative and looking where that second derivative over the design space goes to a positive value, you could very readily determine where the minimum was in that function. In this case, it was a. However, I think that the cartoon here, the graph here on the right, shows that things become a lot more complicated when you have a constrained problem, because the first derivative doesn't necessarily equal 0 at the point where the function is minimum. Like right here, I think is the great example. Here you've got this sort of sharp angle being created by the constraint G1 and the slope of the curve. The little space in here, that's where your minimum is, but you would never find that by taking the first derivative. If you took the first derivative here, you would end up right here, which clearly is not a minimum or a maximum. So because of this, there are people, mathematicians, great mathematicians out there who, gee, I sounded like Trump there for a second, sorry. There are mathematicians out there who over the decades and centuries have researched the heck out of the idea of numerical optimization, trying to find minimum, maximum of functions. There are several methods that have been invented over the years, gradient methods, steepest descents, steepest ascent, genetic search, particle swarm, the golden rule. There's many more that go down here. There's probably 50 or 60 of them that different mathematicians have come up over the years. And I talked to you a little bit about a subculture among mathematicians of people who have competitions with one another to try to figure out how they can design algorithms to more quickly find find maximum or minimum within a function and given constraints. And one of those nerds was Garrett Vanderplotz, and I will introduce him at the end of this lecture. So I want to sort of formalize a little bit the mathematics behind what we did when we played a game last lecture. And we talked about, picking a search direction. We talked about choosing a step, how far you step in a given direction. And that is boring and tedious, but it enables these methods to be very readily translated into computer algorithms, okay, which of course make life easy for everybody, because then you can just throw it in the computer and let it worry about it. So here we have an objective function f of x, and we want to minimize f of x. F of x, the mountain, the sort of topography, the shape of the mountain for f of x is shown here in the black lines. Okay, at this black line, this is the contour, constant value contour for f of x equals to 10. This is 9, this is 8, and we have some constraints, an inequality constraint. The constraint in this case is g of x. G of x has to be less than 0 in order for this to be valid. So the g of x functions are given in blue, and or the contours for g of x, I should say, are given by these dashed blue lines, and then the constraint here is given by this dark blue line right down here. You can see that. Okay. We have a design vector. Okay, so the design vector, I don't know about you guys, but I hated working in vectors as an undergraduate. I mean, I see the value in it, but it took me years to really understand it. It came long after I was actually in class, getting graded on it. Anyway, design vector is just a way of saying the design variables in brackets. Okay, it's just the design variables in brackets. So the design vector is x. It's made up of two different design variables, x1 and x2. We have a two-dimensional design space made up of x1 and x2. The design vector is x, okay, x, and it's made up of x1 and x2. Not that complicated. So the iterative approach of finding the minimum of f of x given these constraints, or given the constraint g of x, is given by this equation right here. And what this says is that you're going to pick a starting point, and then you're going to choose a direction. Sound familiar, guys? You're going to choose a direction to start looking, and then you're going to choose a step. Okay, so we talked about this when we did the game. We talked about a direction, and we talked about a step size. In this case, the direction is given by s. Okay, and step length is given by alpha, right? And we are going to choose a direction. Okay, this could be done randomly. Let's just say that we came out, we just did this randomly. We didn't know what the direction was. There's a better way to do it, but I'll talk about that in a second here. So here's the initial search direction. It's going in -1 in the x1 direction and -0.5 in the x2 direction, right? The search direction is typically best chosen by choosing the opposite of the gradient of the objective function. So what the hell is a gradient besides an upside down triangle? So a gradient is, the sign for gradient is given by this upside down triangle right here. You guys see that next to f of x here. And this is some wonderful tool that some mathematician probably in the 1600s invented, where you can find the maximum of a function. So the gradient always points in towards the maximum of the function. So if you were in a mountain, the gradient would always point to the top of the mountain. All right, it's some wonderful tool. I'm not a mathematician. There's somebody at MIT who can explain this far better than me, but it always points to the maximum of the function. So consequently, if you know where the thing goes up, if you go the opposite direction, it probably goes down. So that's the best way to choose the design direction. And that's the way the algorithms that were programmed by various people, that's the way they choose the direction. They typically will calculate out a gradient, which is some calculus equation with I think it's first derivatives. And they say, let's go the opposite direction from that maximum direction. So the opposite of the gradient of f of x. Okay. Now, so this year I have redesigned this slide to make it a little bit easier to understand, because last year I don't think it was so easy to understand. So this is good. Hopefully this will work better. We're going to choose an initial position, initial location, initial design vector of x1 equal to 2 and x2 equal to 1. And that gets us right here, at this point right here. Okay? That point right there, okay? And we're going to go ahead and start with a step length of 0. Okay, so we plug that into this equation here, and we get this equation here. So basically, we just end up with this vector 2 and 1 plus 0, which gives us 2 and 1. Okay, and at that point, we know, because we have f of x somehow that f of alpha equals 0 equals 10, and in this case, the constraint equals -1. Okay, you see that? So that's the first iteration. Have you guys seen stuff like this before? I don't know if part of the educations that you've had is numerical optimization theory. Anyone? Daywan, you're shaking your head. Nick, how about you? No?
No, I don't think so.
All right. Sheng Hong, are you on the line? Anyway, not sure if he saw this or not, but okay. So then what we do is we pick a different alpha, and we go off in a different direction. So we pick, in this case, alpha equals to 1. We plug that into the equation, this equation here, and we get this plus this, and we get 1 and 0.5, and that gets us to, I'm sorry, we pick alpha equal to 1. So that gets us to right here. We recalculate f of x, and we now know that f of x has gone down. Whoopee. So that means we're headed in the right direction. The function's going down. We're getting closer to finding a minimum because it's gone down. Just like when we were doing that exercise with the function, we knew because the value was going down that that we were headed in the right direction. And we know that at this value of when alpha equals 1, the constraint g of x, or g of alpha in this case, equals -0.2. So one of our constraints was that g of x had to be less than 0. So it's -0.2. We're still good. We haven't blown past our constraint. Okay, and then let's say we take another alpha. We go 1.5. We go alpha equals 1.5. So we step 1.5 units in that direction of the s vector. Okay, we plug that into this equation here, and we get 0.5 and 0.25. We calculate out f of alpha, and whoopee, it's even lower. That's good news. The bad news comes is that when we calculate g of x, or g of alpha, at that alpha equals 1.5, we get 0.2. So as it turns out, we actually blew past this constraint right here. That's a problem. So now we got to dial back. So rather than taking a step length of 1.5, we take a step length of 1.25. Plug that into the equation, we get 0.75, 0.375, and then f of alpha equals 8, and g of x equals, or g of alpha equals 0. Okay, so we now know that that is the minimum. So we just met this inequality constraint of g of x, and we found out that f of x went down from 10 to 8, so that's good. It went down. It didn't go down quite as far as it had gone down over here, but this, iteration 3. But iteration 3 wasn't valid because we blew past the constraint. So this is the minimum, and we put a little asterisk here to indicate that's the minimum. So alpha of 1.25 in the search direction of -1, -0.5, that's where you fit the minimum of this function, and that's the solution to this problem. If you go back and think about like how we did this thing, right? This experiment here, you'll see that we really kind of did the exact same thing here. We just sort of formalized it more from a mathematical perspective. And I'm going to keep beating this home because I really want you to realize this, is that it's not expected that you're going to, with any of the stuff you solve, is probably you're never going to actually have to get there with your calculator and figure this out. Because the beauty of having this put into this formal mathematics is that it then goes very nicely into an algorithm. Okay, and then that algorithm can very nicely be programmed into a calculator or a computer using whatever you're using, Python or Fortran or C+ or whatever you like. And then you can solve more complex problems. And most importantly is that as a human, you're really only capable of understanding maybe a three-dimensional design space, a two-dimensional design space, kind of seeing the shape of the objective function in your head. Like you can only, there's only so much we can understand as humans. But the neat thing is that a computer, and with mathematics, can do all this stuff, with millions of dimensions, design spaces that have millions of different variables, because the mathematics is just the same. It's just scaled up, and I think that's one of the real beauties of mathematics, is that it's so scalable. We talked before when we were looking here, guys. We talked about feasible regions, right? Where is it feasible to have this thing designed? Where can we make stuff? What dimensions can we pick? And just to put a little bit more formality on this, here is a function, a two-dimensional design space of x2 and x1. Here is a objective function f of x in black, and then here is an objective function in G. I'm sorry, this is a constraint and a quality constraint G, with the kind of gray behind it here. Okay, and then if we kind of zoom in right here, here is the gradient f, the gradient of the objective function f that points towards the maximum. And like I said before, we know that usually the best search direction is to go the opposite direction of the gradient. You can't always do that because you'll hit a constraint sometimes, like you see here. But this, regardless, enables us to start thinking of the mathematics behind this. So if here is the gradient of the objective function f, you know that the feasible region is given by this sector, this green sector here. It goes, like 270 degrees or something, or 180 degrees. Maybe sometimes you can go more. Okay, see right there, right? And you know that you can't bust past your constraint. Okay, so, well, I should say this, that the usable region, okay, based on okay, let me take a step back. I didn't describe that very well, sorry. The feasible region is where you don't blow past your constraint, your G constraint. And that's given by this green sector here. That's the feasible region. Just looking at going the opposite direction of the gradient of the objective function, that gives you this blue sector here. Okay, but part of this blue sector is on the wrong side of your constraint, G. So this part here really isn't usable. And that this part of the green really isn't usable either, because it's going the wrong direction. If you're trying to minimize F, then going up is a bad idea. So that means that you're really constrained to this purple region right here. Okay, and then the mathematics behind this, which becomes useful when, like I said, programming, is that the scalar product of the design vector times the scalar product of the design vector S, the search direction S, and the objective function, the gradient of the objective function F, if that is less than 0, and this is some function of cosine, I can't remember exactly what it is. I can look it up, but I haven't gotten there yet today. That gives you some idea of that ends up defining this this blue sector, and then the feasible region, okay, becomes the search direction, the scalar product of the search direction, the gradient of the constraint function G, as a function of x, also has to be less than 0, which then gets you this this green function here, this green sector F, okay, green sector, feasible sector is right here. Then you can sort of see that if you subtract those two, that's what gives you this region right here, which gives you the usable region. So because of what I just said, it starts to tell you, understanding the geometry of these vectors and gradients and the math here and scalar products, it begins to show you or point you towards the direction of what you need, what conditions need to be met in order to know that you have reached a local optimum, a maximum or a minimum, in this case a minimum. Okay, you then know that, because the gradient of the constraint function, and the gradient of the objective function are facing different directions, when you hit a minimum, in this case it's a minimum, you know that those two would cancel each other out. They would go to zero. So that's something that's necessary to know that you've hit optimality, right? So this is some abstract math, and it really, as an experienced engineer, I can tell you this isn't something you're actually going to really encounter working as an engineer. Your chances are your boss is so far away from knowing this stuff or having forgotten this stuff that you'll never talk about it. So don't worry about it. This all goes in the computer, but sort of knowing the theory, I think, is very instructive. It helps you better appreciate what's going on. But you can kind of see if there's some function and you don't really know what this design space looks like, this function f, you don't really know how f is changing in the design space. Okay, you're blind, you're flying blind, you're walking up a hill with a blindfold on. How do you know when you've actually reached your objective? How do you know when you've really reached a maximum or a minimum? Okay, and that's where again where the math becomes useful, and that's where you see this point. Where's my cursor? You see as you start to search in this direction, and you look at the gradient, which in this case is pointing to the optimum of delta g, or the optimum of the constraint g. As you sort of move in the design direction, you can see how the direction of the gradient of the constraint function will eventually point opposite of the gradient of the objective function here. Okay, and that's where you can begin to see like these two things cancel each other out. You add them together, they cancel each other out. Okay, they equal to zero when you add them together, and that's how you know you've hit your minimum in this case. Okay, this is, trust me guys, it took me a long time to sit down and really sort of begin to visualize this geometry in my head and like how do these things really work. So this is, if you're not picking this up right now from just looking at these silly graphs, it's okay. It's not going to hurt your career or anything, but with time, sit back and kind of think about it, because it's interesting stuff, I think. There is this Karush-Kuhn-Tucker condition, which defines the necessary conditions for an optimum. Okay, and it's given by these three factors right here. So first of all, these three conditions. So first of all, the design vector, in this case A. So my fault here, guys. This is my bad. I switched the variables on you in this slide, and I really need to go back and fix this, and I probably will for next semester. But I didn't have time to do it last night. So in this case, W is the objective function. So that was our F before. A is our design vector. That's what we called X in the previous slide. And then G and H G is a constraint, and H is a constraint as well. Okay, so the design vector A needs to be feasible. It needs to be going in a feasible direction. Okay, and then we have these things called Lagrange multipliers. A Lagrange multiplier is another mathematical, beautiful, wonderful invention that you can look up. It was designed, I think it was probably developed in the 1600s or 1500s or I don't know, 1700s, something like that, a long time ago. But basically, it's just a scalar that you multiply times a gradient. So the condition for finding a minimum is that the objective function, the gradient of the objective function at your design value A, okay, your design vector A, plus the sum of the constraints, all those things together equals zero. That's when you know you've hit a minimum. Okay, for maximum, it changes subtly. You change those plus signs to minus signs. So the subtracting out the constraints, the gradients of the constraints times their Lagrangian multiplier from the gradient of the objective function equals zero. That's when you hit a maximum. I've tried to explain that over here in this graph, and you guys can go back and look at this, but you can kind of begin to visualize that when you have multiple constraints, G's and H's, and you have gradients pointing towards the maximum, in this case the maximum, of those constraint functions. When all those gradients sum up to 0, even if they're negative, which is in the case of a maximum, that's when you know you've hit the optimum value, maximum or minimum, of the objective function. Okay, it took me. I mean, I'll be honest. It took me probably years to really get some small little idea of understanding this mathematics here, and how these gradients and vectors and Lagrangian multipliers come together, to how you use all these little items, these mathematical constructs to determine when you're at a maximum or minimum of a function. Okay, these mathematical functions, these criteria for determining optimality, they are all programmed into software, and they use these to do exactly that: determine a maximum or minimum, to know when to stop looking. So you will probably never really encounter these when you use a program like OptiStruct or Genesis or other optimization software. Even there's numerical optimization software that's nothing to do with structural optimization or light weighting. Those software packages all have the Kuhn-Tucker equations or conditions programmed into them. So that's the condition that they will use to determine when they've hit a maximum or minimum. Okay, I could try to take some questions on this if any of you guys are interested. If you have any questions.
Yeah, Don. A quick one. I think so far we all been talking about linear optimization, right? Just wondering if it's common to see nonlinear functions in this kind of application at all.
So I think you're talking about the objective function being linear or nonlinear.
Yes.
I think what I'm showing you here, as far as I know, and maybe you know better. And I'm saying that to sound mean, but I mean I don't know. All of this, as I understand it, is generalized. So f of x can be linear or nonlinear.
I was more talking about linear programming in general. So there's no discontinuity, for example.
Oh, in the function?
Yeah.
Like what happens when you have a discontinuity? Yeah, I think that must be one of the conditions which I left out of this presentation, that the function needs to be continuous. I'm sure there is a mathematician at MIT who can answer this question much better than I can. Anyone else? Nick?
So what we're looking at here is just the set of conditions for a given A star. A star could really be anywhere here. We could apply this set of conditions and figure out if if it is 0, then we are truly at the minimum or maximum. And if it's not, then we apply our algorithm for moving in a direction to try to find the place where this equals 0, right?
I think you got it. I think that's absolutely correct. If you keep thinking of this graph here, and going from right over here and stepping towards the minimum right here, and seeing how these vectors cancel each other out. Now, these vectors will not, most likely, will not be the same length. So they can't truly cancel each other out. But that's what the Lagrangian multiplier does. It's a scalar that you multiply times this vector, which makes it bigger or smaller, so that when you add it to the gradient of the objective function f of x, they cancel each other out. Right? And so this is a simple case I'm showing you right here. This is the more complex case when you might have, inequality constraints, side constraints. H and G are just different types of constraints. And then you can see here, since we're finding a minimum here, and you can see these vectors would cancel each other out at a minimum. At a maximum, you would have to subtract out the constraint gradient vectors from the objective function gradients. See that? And that's why one's minimized and one's maximized. It's a question of which direction are these vectors pointing.
Yeah,
this
I think it makes sense.
And again, this is highly this is highly simplified, guys. This is highly simplified because it's only two design variables.
Yeah, I'm going to have to go out and find a good numerical example of this.
Well, if you want to read more about it, let's see if I can get you this book. Hang on a second. Here, okay. Garrett Vanderplotz books on optimization theory.
Mm-hmm.
You'll see that I've basically lifted most of this lecture from this book or its cousin book, which I've done my best to give credit for, I hope, somewhere. Here we go. Okay. Okay. Good book. I recommend it highly. The people over there at Vanderplotz R&D are very, very nice, and they will work with you to understand the theory if you're interested, because they're just total geeks about these things. So this method of finding the optimum or minimum or maximum of a function is called using a gradient method. Sometimes I've heard it called, method of steepest descent or method of steepest descent, but it's a gradient method. And here is an example, just to show you one more time, just to knock this home, what this might look like. Oops. What this might look like if you had a complex, function here. So you've got these contours right here, and you've got a two-dimensional design space of x1 and x2. And suppose you started right here at x0, right here. My cursor keeps going away. You guys see my cursor? Okay. Right here. Okay, so right here at this point, it's possible to calculate out the gradient of this function. What do we call this function? What the name of this function is? And in that case, the gradient would point this direction. The red arrow is the opposite direction of the gradient. So that's your first, that would be your first direction, your first search direction. And you would pick some step length, which would get you down here to x1. At x1, you would calculate out your function again and see if you've gone down or up. Assuming you've gone down, okay, you would then calculate out the gradient, or the computer algorithm would calculate out the gradient right here at x1. The gradient in this case points this direction. So choosing the opposite direction of that, you go this way, the red arrow again, and you pick another step length. And suppose you pick a little bit bigger step length, and you go down here to x2. And then you can go ahead and calculate out your function value again. In this case, it's less. It's actually in this case less than 0. And then right here, again, you can calculate out a gradient. The gradient would point this direction. Go the opposite, pick some step length, get you to here. This is S3. And then again here, you do the same thing. You calculate out a gradient, which is this direction. You go the opposite direction, and that you pick some step length, and that gets you down to here. And so on and so on and so on until you hit the minimum, which is, I think, right here where this dot is. It's negative 41. So this is an example I lifted out of Garrett Vanderplotz's book. But you can see how using this gradient method, where you calculate out the gradient at a given point, shoot the opposite direction, pick some step length, you can keep doing this over and over again. And I think very rapidly gets you to a solution. And that's kind of clever about this method, is that it works really quickly. And like I said, there's actually conventions where people are really fascinated by this sort of thing, come together with their computers, or they all have some common computer, I don't know. And then, the conference holder gives them some function, and they got to find a minimum or a maximum. And then, they load up their algorithm, everybody presses go at exactly the same time. And then whoever gets to the bottom or the top first wins prize. Maybe it's a bicycle or a trip to France. Anyway, so interesting stuff. This is a whole other world of engineering and science and mathematics, a whole area of STEM that people have been fiddling in for years with great fascination. And like I said, Garrett Vanderplotz is one of those guys who's into this sort of thing. Steve, you look like you have a question.
I'm good, thanks. The reason I look like I have a question is because some of this is just going straight over my head, and I'm doing my best.
Well, it's okay. Our discussion about the Chauvin case went over my head too.
This is my normal face. I'm sorry.
Anyway, just remember, fundamentally, X1 and X2 are design variables. They might be the diameter of a tube. They might be the wall thickness. They might be the length of a square tube. They're just, in this case, when you're talking about structural optimization, they are just geometrical features of a structural member. It could be a head tube. It could be a fork blade. It could be a caliper arm, a brake caliper arm. Okay, and then the weight or the stiffness or the natural frequency, the strength, whatever it is, as you change the dimension of X1 and X2 together, gives you some function, some topography, some function of a curve. And all you're doing is you're using a lot of cool mathematics that was developed in the 1600s or 1700s by guys like Bernoulli or Lagrangian. You're just using this fancy mathematics to find the lowest point in this case, or the highest point, whichever you're looking for, whether it's high strength or low weight, right? And then there's some I don't know, abstract theoretical mathematics, things like the Tucker-Kuhn condition, that lets you know when you've hit a maximum or a minimum. And these are just there. They're just useful in the sense that they're very nicely programmed into a computer, and then the computer can worry about all this for you.
All right, so here's my question. Does this apply both to shapes and thickness? Is it the same analysis?
Does it apply to shapes and what?
And thickness, dimension?
Sure.
Okay. All right,
method is,
that was the reason my face was looking the way it did. I didn't know that it applied to both. I got it.
Steve, just to put this in perspective, these numerical optimization methods were developed on their own. There are people who, like Garrett Vanderplotz and Lucian Schmidt, there's people who decided to apply these numerical methods to structural design. But these numerical methods of finding the optimum, the maximum, the minimum of a function exist completely outside of bicycles or structural optimization or racing cars or airplanes.
Got it.
So there are people in operations research, like there are probably law firms, that would use the same approach to figure out which clients to boot out the door and which clients to take. Right? So your objective function could be money. Your objective function could be money. You could say, where is the highest point on my graph here, on my three-dimensional, multi-dimensional hyperspace, where I make the most money? The top of that mountain is making the most money. And then your design variables can be your different clients. You know, this client has a lot of money, but it's a short case. This client doesn't have a lot of money, but it's a long case. You could, I'm just showing you the flexibility. I'm just trying to demonstrate the flexibility of the method.
Thank you for explaining it so I can understand it. Is there a variable there for being able to tolerate their personalities?
That's the thing. You could find some way. Like you could have some objective function. Like, you know, you have some function annoying to the squared plus irritating to the third, equals annoyingness.
Yeah, exactly. An annoyance function. Got it.
Right. I don't mean, by the way, I'm not trying to say that lawyers are only after money. I didn't mean to sound annoying. I'm just giving it as an example. I don't mean that at all. I don't mean to be.
No more than engineers.
No more than engineers.
That's what I was going to say. Most people are after money. That's what we work for.
Okay. I don't have any grudges against lawyers. I don't buy into the stereotype. None of that. I'm just trying to give you an example that this method, how general it is and how fluidly it can be applied to many different conditions. Like airplane companies use the same thing to like figure out, you know, which routes to pick. You know, which routes, Chicago to New York or Boston to Los Angeles, like which of these different float routes will give us the most money or make the most customers happy or whatever it is.
That's okay, Don. I once had an economist sit me down and mathematically show me how lawyers detracted from the economy rather than added to it. So,
well,
used to it.
Did he factor in intellectual property and, you know, keeping good people out of jail? I mean, I don't know. People make lots of.
They all sound that way until they need a lawyer. So, you know, I take it with a grain of salt.
Okay. Well, just so you know, my uncle is a lawyer. One of my favorite relatives is a lawyer. So.
Okay. I think when you said in the beginning there are 50 different optimization techniques, I would estimate between the Sloan School, the electrical engineering department, the civil engineering department, and the mechanical engineering department, there are probably 20 or 30 faculty at MIT who specialize in optimization of different things mathematically.
Right.
And that doesn't even include the math department because I don't know those people. Okay.
Well, I'm just, like I said, this method was developed outside of racing cars and racing bicycles, and it's very, very easily applied to many different topics. It's very flexible. It's very interesting because of that to me. Okay, there are other ways. I don't know. I'm just want to get through these next couple slides here real quick here since we're almost out of time. But there are other optimization methods out there besides gradient approaches. One of them is called genetic. There's one called genetic search, where you sort of mimic nature and evolution. And with this method, what you do is you have a population, and this is really abstract. You have a population of different designs in your design space. Okay, you've got this individual who has this wall thickness. You have this individual that's got that wall thickness. You got another individual who's got a third wall thickness. Some complexity, some number of design variables, and you represent these individuals as a string of numbers, of zeros and ones. And then you can have you choose many different members of this population over your design space, maybe thousands or tens of thousands, maybe even millions. And then you find somehow you randomly select, I guess, different members within these design spaces, and you have them mate. Okay, so this is they're both consenting. Okay, they mate, they have offspring. Okay, and then these offspring have their own combination of zeros and ones. The offspring are not just a strict. There's like these algorithms for mixing the parents to come up with the offspring, and then there's like a they call it crossover, and there's a mutation, and you come up with a little bit of random input, a little bit of random stochasticity, and a little bit of stochasticity to determine the string of numbers that defines the offspring. And then you plug those design variables from the offspring into an objective function and come up with a number. Okay, suppose you're trying to minimize, in this case, just for example, if the objective function shows that those offspring individuals led to an increase in weight, then they will get a penalty function. If it shows that they led to a decrease in weight, for example, then they will be bred with each other, for example, or another set of individuals that got to a lower weight. Okay, and then you'll end up with those two individuals, consensually having another set of children, right? And those set of children will be judged on whether they increased or decreased the weight of your structure, for example. Okay, so this goes on and on and on and on until you come to some point where you're not the weight isn't changing much. It converges, as they say. It converges to a value. This is a method that has become more common, genetic search methods. And then another kind of similar method is this particle swarm method, where they call it seeding the design space with many individuals, and each individual gets a design direction, a design vector. And then at time step 1, all these little individuals, all these bees in this multi-dimensional design space move in a direction. And then for each one of those, the computer will calculate out the objective function after they move some direction. Okay, and then the directions that produced a good result, meaning in this case a lower weight, will move again in that direction. And the ones that didn't will get a penalty function and get heavier. And then on and on and on, and all these different vectors going all these different directions until finally you converge to a minimum. In this case, if you're talking about weight, for example. This is a little bit newer method. Effectively, if you think about it, the genetic search method and the particle swarm method are actually very close to the same thing. So these different methods, by far the most common that you'll find in the softwares out there for numerical optimization or structural optimization or gradient methods. And Gradient methods are probably worse at finding a global optimum, but they're a lot faster. Okay, so they're used. There's pluses and minuses to using to each of these. The particle swarm, the genetic search methods and the particle swarm methods are very good at like I said, finding those absolute optimum minimum within a design space, but they're very computer intensive. They take a lot of time to converge. So depending on how exact an answer you need, then you might use one method over another. So for example, like if you know that you're designing the wall thickness of a top tube of a bike, but you know that you can't actually measure the wall thickness of the tube very accurately, then it doesn't make sense to invest the time and money in using a genetic or a particle swarm method, because you're never going to get that granular anyway. So you might as well just use a gradient approach. Okay, Moore's law. So Moore's law stated that computers would double, or you'd be able to get, twice the number, an order of magnitude more transistors on a chip every 5 years or every 2 years or something like that. Maybe someone knows this exactly more than I do. But I just wanted to show with this slide that the people who develop numerical optimization software like Vanderplotz, they have very nicely taken advantage of these increases in computing power, cheap computing power. And it shows, just wanted to show how these graphs roughly copied each other, mimicked each other, and that as computer power has gotten cheaper and faster, the numerical optimization people have been able to write better algorithms that take advantage of these increases in computer power and increase the efficiency with which they can converge their optimizations. And then finally, last slide for today, I want to introduce you to Garrett Vanderplotz. Garrett Vanderplotz is the founder of Vanderplotz Engineering. He was one of Lucian Schmidt's graduate students. I think at Case Western Reserve, this guy was Lucian Schmidt's graduate student. And he worked at NASA after he got his PhD in structural optimization, and went to work at one of the Navy schools. I don't think he was actually ever in the military. I think he just studied there. He was a professor at University of California, Santa Barbara for a long time. And then I think he got sick of the politics of being a professor and decided to start his own company. So in 1987, he launched Vanderplotz R&D, and they are the publisher of a software called Genesis, which is one of the first structural optimization softwares with a graphical interface, which I've used many times. Great software. I like it better than OptiStruct personally. And he is one of the nerds of the nerds, the nerdiest of the nerdiest when it comes to these optimization competitions. So this is the guy that packs up his computer and spends all night writing, he spends all night developing software and developing algorithms for finding optimum faster than the next guy. And then he goes to these sort of conferences where they all sit down in a room and have competitions to see who can get their algorithms to find the optimum or maximum or minimum the fastest. And let's see here. He's also kind of a car guy. I met him a couple times. He has this old Mitsubishi that I guess he rebuilt for fun that he always talks about. And he lives in Monterey, so he's got good taste in geography. Anyway, you should. The reason I'm showing you guys these different people is just so if you want to learn more about a given topic, you can go to the library and then you can search under this person's name, and then you can find more articles. And I've got a stack of articles somewhere written by Vanderplotz and his graduate students at UC Santa Barbara that I read many times over the years and I found really interesting. And like I said, he's just I don't know, he's just diehard, hardcore. People soup up their cars and have races. I once knew a guy who spent his leisure time souping up flashlights for competitions to see who could come up with the flashlight that shined the brightest without burning your hand off. And this guy's that way with numerical optimization. It's just his thing. That's what he does, for fun. It's like the material science professor's got an X-ray diffractometer in his basement. This guy just sits around on weekends writing algorithms for making faster and numerical optimization software. And he comes up with Big Dot and Bigger Dot and the Biggest Dot. Those are the names of the softwares. Anyway, I'm beginning to babble, so I'm going to stop. But if you want to learn more about numerical optimization, I recommend highly that you go to the library and look up Garrett Vanderplotz. Any question, guys?
I just had one question about on the gradient method, how step size was determined in that last example that you gave, or maybe it was kind of random, or just like how in general step size might be determined in that situation.
This has to do with that topic of convergence that I mentioned. So the computer algorithms will calculate what percentage increase they're getting. And when that percentage increase starts to slow down, the step sizes it chooses will decrease. So in the starting, why not gamble a little bit? Take a big jump, and that's what they do. Okay. So in the beginning they look for big home runs, and they typically use bigger steps. I'm sure there are softwares out there where you can adjust the size of the step, and maybe you cause it to have some constant step or something. But as I understand it, talking to my friends at Vanderplotz, there's something in their software that adjusts the search direction step based on how much the function is changing. The objective function is changing.
Okay. That makes sense.
Oh, you are there, Sheng Hung. Have you been here the whole time?
Yeah, I'm checking the book that you recommend.
Yeah, here, there's, let me get the other one here. There's, hang on. This one's also about the same book, but a little bit newer.
Let's see. Cool one.
You see?
Yes.
They look boring as heck because they're just these sort of generic looking.
Wait, let me take the screenshot.
Take the screenshot. Go ahead.
Because
By the way, I'm not collecting. I don't have any financial arrangement with Vanderplotz. I'm not collecting any money off of this.
Cool. Got it.
Okay. Anyway, great books. Any other questions? We're good until next week, guys? Okay, next week we start getting into finite element analysis and some of the T tools, topology optimization, topography optimization, et cetera, et cetera.
Thank you, Don.
Don.
You're welcome.
Thank
See you guys
you.
next week.
Sounds good. Thanks,
Have a good
Don.
week. Bye. How's it going, Steve?
I just want to say thanks for explaining it so even the slowest